Okay, so hello everyone. My name is Itai. I'm from a company called Footer, and today we're going to talk about flaky tests. So what are flaky tests? Flaky tests can fail or pass for the exact same configuration. So what do we usually do? We just try to patch them and go on with our next item on the list. We don't usually stop and think about what is the underlying problem here. And so after you patch the test and then it fails again, you need to test the patch of the test that you just patched of the test, because you're not really sure if you fixed the problem or not, because by definition it happens sometimes. And if you have a complex enough service, it will happen more often than not, and that's going to be a big problem. So more often than not, the underlying problem of flaky test is the assumption that each test has only one correct answer. So while in reality, the test could have like a range or even a spectrum of correct answers, and you need to account for that. And the reason I want to mention confidence is because of our customers. So our customers are enterprise e-commerce merchants, and they probably, today they know who Footer is, but if we go like 3 years back, it wasn't a common brand. And so they would ask us, how do you prepare for Black Friday? Black Friday is the days when they have these promotions and they make most of the money. And the expected answer would be that we would tell them we do code freeze 1 month in advance, but no startup does that, right? So the answer we do give them is that we have a lot of confidence in our system, in the tests. And so we project this confidence to our customers, and we say the fraudsters, I'll explain in a minute. Footer provides basically a fraud prevention solution for e-commerce merchants. So this is an adversary environment in which the fraudsters keep on trying again and again and again. And so the fraudsters, they never sleep. They never, they keep on trying. And so we cannot just code freeze. We need to keep on evolving. And so the tests provide us confidence in 3 different phases in the development, right? Obviously during development, and then during deployment, we usually have these pre-flight checks. We're gonna go over those. And then when they run continuously in production, we usually call them probes or monitoring or stuff like that. But basically I would call this whole family tests. And the main theme of this talk is about confidence. Okay, how do we gain confidence? So first, I'm going to give a little bit of context, because I'm going to use like the same example again and again and again. And then we're going to talk about flaky unit tests due to precision and accuracy problems. The second example is going to be about flaky integration tests, because the system being tested is non-deterministic. Okay, I'll repeat that again. You have a system. Each time you test it, you get a different result. You can see why that could result in a flaky test. And then the last one, we would talk about flaky system tests that are caused due to asynchronous data pipeline hiccups, which is, again, a normal thing, but it can cause a lot of trouble. And you would see that each one of the solutions I'm going to propose, we basically bend over backwards to fix the tests, and it requires a lot of investment. So you might want to try it or not, but you need to keep track of the requirements of why we did such a great investment in order to fix it, because this might be relevant to you or not. So let's start some context. So as I've said, Footer provides a fraud prevention solution for e-commerce merchants. So think 5 years ago, you go online, you shop for something, you press the checkout button, you fill in the shipping address, like your home in Israel probably, and the billing address, which is usually the address of the credit card holder. Usually it's the same address. And then you click the buy now button, and they said, we're sorry, we never saw an Israeli credit card, maybe you're a fraudster, please call customer support, or we don't support shipping to Israel. all those kind of things. So this was, I think, let's say 5 years ago. Today, every e-commerce merchant has their own, either they partner with companies like Footer, or they have their in-house fraud prevention team. So how the system works. The raw input is the billing and the shipping address. This is like text. And the output is a decision. Either you decline the transaction or you approve it. So this is how the game works. If Footer approves a legitimate transaction, we get a cut of the deal, which is very nice. If we approve a transaction and later on it ends up being a fraudulent transaction, for example, it was someone using someone else's credit card or an identity theft, then Footer needs to repay the money to the customers. And it becomes very, very tricky because let's say we want to decline more transactions. What happens is that the end users, they get like very angry because they cannot, check out. They start calling our customer support and so on. And then we get calls saying, what are you doing? We cannot handle all these customer support calls, right? And if we approve too much transactions, then too many fraudsters would, come in, and then we'll have trouble because we need to, reimburse our customers, and they would have trouble with the credit card issuers because saying, listen, you reached the maximum amount of, illegal transactions, fraudulent transactions, and so on. So there is like a very narrow band where we operate. So how does the system work? So we get the raw data. The first thing, we need to process it. Okay, this is where we're going to talk about unit testing. So in this example, we designed a feature which is called billing shipping distance, which is the distance between the billing address, the credit card holder address, and the shipping address, and the result is in miles. And then the next component is a fraud prediction, which is a machine learning component, which makes things more interesting, as you'll see soon. And then the last component takes the fraud probability and then applies, customer-specific policies and outputs a decision. In this case, the billing shipping distance was 1,200 miles. The fraud predicted it's a 25% fraud probability, and the policy is that if it's above 20%, then decline the transaction. Okay, so this is the example I'm gonna, hammer in this presentation. So let's start with flake unit tests. If you phase out, then phase in again. You can see the top right corner, like it says unit test, so you know which example we're at, what I'm talking about. Floating points, yay, precision. Quick question, how many of the Hebrew speakers in the audience know the example between precision and accuracy? How do you say precision in Hebrew? Diuk. How do you say accuracy in Hebrew? Diuk. So people get confused. So let's say I say pi equals 3.1. So this is very accurate, but not very precise. If I say pi equals 3.55555, I'm very precise, but it's not accurate. If I say pi equals 3.14159265535, then I'm both precise and accurate. Okay? So now we're talking about precision. Most developers eventually find out that floating points have this precision range, and it was designed to have a very high range of values, but it loses accuracy. That's like the basic trade-off of floating points. And so when you go back to the example where we want to measure the distance between 2 points on Earth, this is an example I copied from the README file of the GeoPy library, and when you run it, you get this error, right? Because there's a precision difference. So developers usually, when they see such an error, they're like, yeah, whatever. That just plus minus 0.01 miles, and let's go on with our lives, right? Problem solved. Yay! And then, I think, if I remember correctly, it says on the 7th of April, 2018, the default distance algorithm in the GeoPy library was upgraded to a better one. It is more accurate now. And so I came happy to the office. I called the relevant fraud analyst. Listen, we have like a new version. We have to upgrade. And he was like, yeah, whatever. And I upgraded it, and our test failed because the expected result wasn't the right one. So this time I was like, okay, I'm not gonna patch it, right? I called the analyst, and he was like, who cares about 0.01 miles? It has no meaning from fraud analyst perspective. So we changed it to be plus minus 1 mile, or if it's a really big distance, then even 1%, in this case, like plus minus 5 miles is okay. And that got us thinking that developers should not be maintaining these tests at all because they don't have the domain-specific knowledge. And this is not just a problem with, geodistance. If you think about reputation, it's a range, okay, it's a spectrum, and it can change. And then the unit tests keep failing, and you see like fraud analysts every day coming to work and copying, like they have this assertion error in the CI, they copy it, and then they copy the result of the test, and then the test passes, and they waste their time doing this again and again. So we designed this very slim test wrapper that basically allows analysts to put the raw data inside. It's easier for them. And then we have this approx, like TSL language if you want, or you can specify one of these options. And this is how most of our unit tests look like. So it started with flaky test, but eventually the basic confidence in our system was broken, and we had to fix it in a more basic way. So this was easy. This was like warming up. Okay. Next in line, integration test. So I would like to test this whole flow. And this flow, as I'm gonna prove in a minute, is non-deterministic for the same input in my result in different results. And why? Because all of these features, they depend on microservices. It could be, as we saw in Nitzan's lecture, it could be like internal microservices that are external to this service, or they could be even external to your company. And so what happens when the geocoding service fails? So we need still to give some kind of result, right? So almost every feature has like this fallback mode. So in this case, instead of saying the billing shipping distance is greater than 1,200 miles, the result of the feature is it's greater than 100 miles because we see they're like in different states or something like that. And so an exception is raised, and this is very important. So just hold that in your head for a moment. And the fraud prediction, it got a slightly different input, and it provided a slightly different output. But because of the policy, the test now fails because the expected result is decline, while actually sometimes it's flaky and it returns a proof. But there's nothing wrong with the system that we are testing, okay, which is everything except it's everything except the blue boxes, but it includes all the arrows, right? It's an integration test. So let's analyze what's going on here. There's a basic trade-off in integration tests. You want stability and you want integration coverage. And so on the far end side, you could say, this is what like most new developers, they're like, you know what, let's just stop everything. Don't call any other service. Redis will just pip install fake Redis or whatever. And then each other service will write a stub or a mock, and then you say, and then the test will always pass. Yeah, great, but what is the integration coverage? You didn't test what you wanted to test. You will eventually end up in production, and you will in production with many exceptions, and that you could have caught earlier in the integration test. That's the whole point of an integration test. So at the other end, you can connect to other services always. So the integration test, each time it wants geocoding, it calls the geocoding microservice. And the problem is that sometimes there are exceptions, like we just saw. And I wonder, like with a show of hands, how many of you have at your work at least one environment? Let's say the production environment, right? Everyone has a production environment? Okay. How many of you have like two, let's say production and test? Okay, do you have three maybe? Okay, 4? No, okay. So, you do have like 3 people raise their hand. So the problem Okay, so we have 1.5. We have production and we have a developer. You can call it test environment. And the problem here is fatigue. Okay, you cannot, production environment, if something breaks, you need to run and fix it. You cancel whatever meeting you're at or whatever you're at lunch or whatever, you just go on and fix it. But you don't want to double the stacks by 2 and by 3 and by 4. It doesn't make any sense. So in the test environment, it's okay, to go for the meeting and maybe fix it when you're back or fix it tomorrow morning. And that leaves us with integration tests that sometimes get exceptions. So what do we do with that? What you don't want to do, you don't want to add just slap on retries. This is just like patching the unit test, because when you add a retry to a test, usually it adds up. I mean, the time of the test when it fails gets much longer, and it assumes that the problem is temporary. So the geocoding service didn't work, and now 5 minutes later someone fixed it? No, that's not what actually happens. So what we did, okay, so one way of approaching it is going from the left side to the right, and basically you say, okay, I'm not going to use fake Redis, I'm going to install Docker Redis on the local host. And this is, I'm not going to call the GeoPy microservice, I'm going to install a GeoPy Docker on the local host. And so it makes sense if your system is relatively simple, but if you have, 10 microservices and each one of them recursively requires, a database and special configuration and more Dockers, then each test suite would require, like 20 or 30 Dockers to start, and this would not hold. So we'll go from the right up. So the first thing that we do you remember the exception monitoring code? We mock it during tests, and we just log. Every time there's an exception, we say, okay, exception. We write it down, and then at the end of the test, we take the list of exceptions, and we look at them, and they say, oh, this exception, it's not because of us. It's this other service failed, and probably would get fixed tomorrow morning, so it's okay. So we let the test pass. Don't get angry. It's like, people looking at me strange. This is what we do. A test has an exception, and we say, okay, it's okay. But this doesn't really solve the problem, right? Because there is an assertion line that says decision equals decline, and now it's approved. You cannot just delete the assertion, right? Yes, you can. So our integration test does not have an assert on the end result of our system. Okay, yeah, we have an integration test that always passes, almost have really good coverage and really good stability, but we don't actually test the one thing that we get money for. So what I'm going to show you now is this whole big operation just to test that assert. This basically shows that, reminds us that this decline decision is something that we send back to our customers. This is where we make money. And so we said, okay, we don't have a really full-fledged testing environment. Let's test it in production. Yay! Do you know what bird is this? The canary, a songbird, very beautiful bird that in the old days coal miners would take with them down to the coal mine. And other than singing, this bird is very sensitive to lethal gas. And so when the canary stop singing, they just git revert and get out of there and get back home. And this is like the metaphor for a canary release. This is what Netflix, if you're a fan of Netflix blogs, you would see this a lot. Basically how it works, I'll go over this quickly. You have an existing production environment, and then you install the version 2, let's say only 3 instances. You don't want to sacrifice too much traffic, but you connect it to the same load balancer as the production. And then you want to compare metrics between the canary environment and the production environment. The problem is that they were not born equal, right? Because the production environment already has all the caches, all the connections. It is much, much scaled out. And so it doesn't make much sense to compare the canary release to the production. So what they do, with the canary, they also deploy 3 instances of version 1. They call it baseline. And then they compare the results of canary and baseline. Okay, does this make sense? And they also now have like this spin-off, this open source Spinnaker.io that lets you do all this deployment, and they have this new Kayenta features, which does the automatic canary analysis. You can just take it and use it. We don't. We don't use it, and this is why. Loss, money. Okay. So wait. This is complicated. Just look at me for a minute. We lose money all the time. Okay. Sometimes fraudsters are able to get through, and this is part of the cost of doing business. It's not something we can control too much, at least not in the short term. Engineering loss is something, this is like what we call analytics loss, but engineering loss is when a machine fails and then we switch to fallback mode, our results are not as accurate, and then we lose money. Again, we cannot prevent instances from failing, right? So this is engineering loss. But there's another factor for engineering loss added by a canary release cycle, which we can control. So there are two things to observe here. There are minimum number of transactions needed before you can have a statistically significant result to compare the canary V2 with V3. Okay? It takes usually, let's say, 10 minutes, 15 minutes. It really depends on the throughput, right? So this is a number. This part you cannot reduce it. And then Netflix, for each, let's say, transaction, they would probably give a wrong recommendation or some kind of hiccup with the video streaming that I guess they could, they have probably local caching, so no one would even notice. But at Footer, we handle flight tickets, jewelry, shoes, food, and other expensive stuff. And so we cannot afford this to let the canary, stop singing. Too much money. And so we use blue-green deployments that we call affectionately effectless, which is, I'll show you in a minute. So the green environment is now in production, and we want to deploy V2. So we deploy a complete, fully scaled deployment. This is the one in blue, and it starts with a toggle that we call effectless equals true. Okay, so the blue environment is different because of this little toggle. And so the first thing we start doing is, do you remember the integration test from before, which basically sends bogus transactions and checks for exception? We do that here again, just to warm up everything, start the connections, make sure there are no serious exceptions. Now we do care if it's not able to connect to the geolocation microservice. And then we send a copy of the real traffic, we just read it from the database in a short delay, to the blue environment. And the reason we need this toggle is so the statefulness of the blue environment would not conflict with the green environment. So basically, instead of writing to an S3 bucket called production, we write to an S3 bucket called effectless. Or instead of writing to this table, we have like this underscore effectless table. So it is very slightly different from production, but it handles the same traffic. Okay, it is scaled just as much as production. We try to warm it up, and now we can compare between the two environments. And this is where it gets tricky. So do you remember this guy, the architect from the metrics? He told Neo, some of my answers you will understand, and some of them you will not. So I'm a developer, I'm an engineer, and I look at the results and they're not the same. The blue env and the green envs are different. And I'm like, I have no idea why the machine learning decided to accept this one and decline that transaction. The machines, the trained machine learning model is much more, is much smarter than the average or above average engineer when it comes to fraud prevention. So we call the prophet. Okay, we call the fraud analyst. And this is also a quote from the movie. You've already made your choice. You're here to try to understand why you made it. So this is how it looks like from an engineer's perspective. You get this report on Slack that says that decisions are different between the effectless and the production environment. The API latencies are great, the exceptions are great, but there's a problem, and I would advise not to switch. And then what you usually do, you call an analyst. Okay, because maybe the blue environment is even better. Maybe we fixed something. Maybe the precision just got better. So an analyst can go over all the diagnostics and all the transactions, and together the developer and analyst figure out what went wrong or what is better. So this is like the downside of this approach, but it is much, much safer, and this is how we gain confidence in each version we deploy. And so the next step is to drain the green environment, and then we still leave the green one as fallback, because 15 minutes is usually not enough to understand all the problems, and we have like separate BI monitoring against thresholds, and we check that the blue environment is really, really good from a business perspective. And then about, let's say, 4 hours later, we're back to where we started with the new version in production. Yay. So if you ever want to implement that at home, so this is when you need to remember, small problems will slip through and accumulate. That's going to happen because after 14 minutes, there's some statistical insignificant changes that you cannot catch. So the way to mitigate that is usually to group the statistics by host, okay? Maybe it's just one host that does a problem, or by tenant. Maybe it's only specific customer that this change we applied has problems with. And then even with even if you look globally at your problem, it looks fine, but then when you zoom into a specific customer, you see that all these customers' decisions is always approved. And so API latencies, if you ever compare API latencies, start with the median latency and then go up to the 95th percentile latency. Usually you will see a flat line. But if you try to compare 99th latency, you can do it, but that requires some processing because you will see all kinds of spikes. Don't even bother with the maximum latency. And the last thing is about exceptions. It's not realistic to accept 0 exceptions with new features. Okay? Don't even try. So what we do, we have like this features that we expect them just to work because they've been in the system like forever, and there are new features, and we have like these thresholds that we try to keep pushing down, but don't try to get to 0 exceptions. It's not realistic. Okay, last one. Are you ready? This is like the more difficult example. So actually, we don't have only one service, which is a decision service. We have many services. Here you can see the analytics service, which is basically a reporting database, a dashboard, UI. So the fraud manager and our customer's fraud manager can look at what's going on in their business from a fraud perspective. And this is important because one of the key decision makers of choosing our solution is now looking at data from the analytics service. And then there's the billing service, which basically once a month issues an invoice. And again, the customer's, let's say, CFO or director of finance is looking at the output of this service. And so the key decision makers are looking at these two services, and if we have a mistakes, it's going to be really, really embarrassing. Okay, really embarrassing. So as I've said, we're going to bend over backwards to increase our confidence in these two services. So as microservice goes, each microservice needs to have their own database, right? You want to separate the teams or separate the code, separate databases, and then you need an asynchronous data pipeline to sync between them, obviously. Let's say it's a publish-subscribe pipeline, and so each time the decision service gets a transaction, the analytics reporting database gets updated, and also the billing database note that a new transaction has arrived. So at the end of the month, we can create a new invoice. And so the first thing you can see is that the different services have different latency or eventual consistency requirements. And we're using the same data pipeline for all of them. And after once or twice that the engineering got embarrassed by these kind of mistakes, we tried to perform a naive system test, which basically what it does is you send a transaction and then you wait 15 seconds, maybe 60, and then you query in each other of the services and want to check that their database is up to date and there's no embarrassing mistake. So does this work? No. Why? Because asynchronous data pipelines have hiccups. Sometimes you get like a burst of traffic and the queues start to fill up, and then it doesn't take 15 seconds. It takes 60 seconds, and that's okay. This is a healthy state of the system. But the test fails. So you can try to increase it to 60 seconds or 600 seconds or patch it or whatever, but you wouldn't get to the bottom of the problem. So the real solution is another service that does reconciliation. The reconciliation service has access to all three databases. Yeah, okay. All three databases, and it just does different select statements. For example, select maximum time, or select the latest transaction IDs, and it just compares them and issues an alert if something is wrong. And in this service, you can configure different SLAs for different databases and different services, and you have much more flexibility and confidence in the results. So the basic two problems you want to check is for missing data, okay, and referential integrity problems. So think about transactional semantics. Some customers, they issue an order and then they issue like an update. Someone decided to change the credit card. And some other customers, they issue an order, then they cancel the old order, and then they issue a new different order, but it's basically the same, transaction. And so this reconciliator needs to know all this and make sure everything is in check. Basically, it has only, it's a green, everything is okay. Red means there's a problem, we need to fix it. So, and this is where we got really motivated. We said, why should a human fix it? Maybe we should have the reconciliator fix the problems for us. If it finds something wrong, it should reach to the right service, which is the system of record for this specific object, and then resend it through the data pipeline. So this is what is called, like, generally in control theory, a feedback loop. And after this lecture, I invite you to log into Wikipedia. Well, you don't need to log in, just go to Wikipedia and look for positive feedback. This is one of the most scary reads you would ever have. It talks about total system meltdown and Armageddon, and this is why. Imagine that an analytics service takes 100 milliseconds to process a transactions usually, and if it's a really, really big transactions, it takes 10 times, let's say 1 second. And so usually no one cares, right? Once every few hours you get a really big transaction, or even once every minute, it doesn't really affect the performance of the analytics service. But let's say you had a bug that all the big transactions failed, and the data reconciliation service decides to resend all these big transactions again. Effectively, it clogs the analytics service, and then there are more missing transactions, right? Positive feedback. And the reconciliator tries to send more and more again and again and again and again. Yeah, so this is what that Wikipedia article meant about total meltdown, and obviously it happened to us once. So what do? You keep on reading in the Wikipedia article, and it says what you need to do is filtering, limiting, damping, and negative feedback. It doesn't explain what this means. So let's try to think together. Filtering means you don't need to fix everything. Some objects, it's okay, they would be out of sync. They have no business meaning, probably some kind of internal flags, test data, or something like that. Limiting means that you don't try to fix the same problem more than once. Okay, makes sense? damping. Do you remember damping from auto-scaling groups in Amazon? Damping means that once you fix a problem, you wait for 5 minutes. Don't do anything. Whatever you do, don't do anything. That's damping. So this reduces the positive feedback. And the last one, this is like the best solution and the most difficult one, is negative feedback. So the way you can implement negative feedback is by monitoring the analytics service. And if it's unhealthy, then you don't try to fix it by sending more data. So the simplest way to implement it is just to look at the input queue, okay, of the analytics service, and if it's above a certain threshold, the reconciliation service needs to wait, okay? Do nothing until the analytics service is healthy again, and then, slowly but surely keep on sending new data. And then it works, okay? And this is how, to wrap things up, this is how we gain more confidence in our data, in our system. So we'll take questions now, right? If you want, it was like a little bit too fast, everything I've just said, we published it yesterday in our tech blog, so feel free to check it out. Yeah. Okay, so the question is, how come the two versions can basically work under the same assumptions, right, with the same databases or the same state?
You have workers, or you have like a search engine. Each of those has its own kind of status, its own queue, its own Elasticsearch. You need to index the data, which is relevant to that database at the time that you start sending the imitated traffic.
Yeah, so here's the thing. Both the effectless version of the green version and, the blue version and the green version, they both use the same databases, exactly. Okay, for reading at least. And so maybe the green version changed something, and then when the blue version tries to handle the same transaction again, it wouldn't see the same state that it would have if it were the green version, right? Is this a scenario you're talking about? Because it's not a fair comparison. And so, yeah, it's true. In this specific service, this is how it works. So we try to ignore some of the hints that was left by the green environment when we run the blue environment. But as for caching and for some of the more deep analysis, the blue environment sometimes is even faster, and it's much easier for it to work because all of the hard work and all the caches and all the state changes probably hinted what the right answer is for the blue version. So actually the blue version has a better chance of getting the right answer than the green version, because most of the answers to most of the questions about the transaction are already in the database. And so, yeah, you're not comparing apples to apples, but this is the best we have. So you need to mitigate that in your code. We're trying to make this effectless toggle as light as possible, and we just say, okay, if it's not a big change, then we will just let the new version through. Yeah.
Reconciliation service, does it look directly inside of the database of the Microsoft?
Okay, yeah, so I skipped a few slides. If you saw, one of them is that your engineering peers will most likely be against breaking the isolation barriers between different microservices. And this is true. It just makes the reconciliation code easier, just to select mux, whatever. And so what we do to mitigate that, we require a unified schema repository. So if one database has a column called tenant ID, and it's an integer, the other database would not call it tenant number and make it a string. Okay? And then same thing for timestamps, that you have like the customer timestamp, our timestamp, update timestamp, cancel timestamp, all that. So all need to have the same name and the same type. And so at least you are somewhat decoupled from some of the implementation. But it's just so much easier to write it with one SQL statement than, or Elasticsearch query, and it's worth it. So what Ellie asked is about how do you make sure that reconciliation service does what it actually needs to do. So the reconciliation service is the test itself. If you want to write a test on top of the test, you could, But reconciliation service requires a lot of experimentation. And so at first you start like with a dry mode. It just outputs what it would have done. You basically test it in production. You could write tests for the tests, but at some point you need to stop. So the reconciliation service basically looks very much like the system test. It just continues, and it has the specific service configuration and has direct access to the databases. So the implementation looks very similar. It's even simpler. So there's less chance of a bug there. But yeah, it requires some experimentation. Okay, thank you very much.